Hi, Ray. So here's an example for you. Let's let G equal the 3 cycle A, B, C. Oops. A, B, C. And to tie it down, I'm going to let the tie down bars have endpoints X, Y, Z. And I'm going to think of these X, Y, and Z as pins that are like pinned in place, right? So pin, like, pins in corkboard where the other things are like joints that get to rotate. So I want to show 2 different ways of distributing these 3 tie down bars. So in the first example, I'm going to put the 2 tie down bars at one vertex and 1 tie down bar at another. And so, for example, because of symmetry, there's really only one interesting way to do this. All the rest are the same. So maybe I'll put the X and Y tie down bars at A and the Z tie down bar at B. And now I have to orient this graph in such a way that every tie down bar is oriented away from the original graph, and every vertex in the original graph has out degree 2. So every tie down bar points away. Maybe I'll write that. Points away from G, and every vertex of G has, out degree equal to 2. Okay, so let's see how many ways there are of doing this. So I'm going to copy this and orient a duplicate copy of it. So I'm going to change my pen color to red and follow these rules. So first I'm going to orient all the tie down bars away from the original graph. So I get that orientation. And now I have to make sure that every vertex in my original graph has out degree 2. And when I look at A, I see it already has out degree 2 because it had 2 tie down bars. So there's only one choice for the other edges incident at A. Since A already has out degree 2, I have no choice but to direct all the other edges incident at A inwards. Okay, but now if I go to vertex B, I see it already has out degree 2. So I have no choice but to do that. And so then I can say I've oriented all my edges and I had no choices. So here I'll say that all edges oriented with no choices possible. And what does the rigidity matrix look like? So there are vertices for A, B, and C. Those are 2 columns each. And so the rows look like A minus B, B minus A, the 0 vector. Maybe I'll, and A minus C, the 0 vector, C minus A, and the 0 vector, B minus C, C minus B. So that's the rigidity matrix for G. And then with the tie down, I need to add 3 more rows. And I've tied down, put 2 tie down bars at vertex A. So I get things that look like A minus X, and then 0 0, and a minus y, 0, 0. And then the last tie down bar is just at vertex B. So I get 0, b minus z, 0. And so now I can see that this is a, even though it looks like it's sort of 3 columns, it's really 6 columns because each vertex has 2 coordinates. So this is a 6-column matrix, 6 columns, and I also have 6 rows. Okay, and then you could put something like this into MATLAB and take its determinant. The other example I want to show you, so example 2, is where I take a different tie-down configuration. So here, instead of distributing the tie-downs 2 at one vertex and 1 at another, I'm going to put 1 tie-down bar at each vertex. So I have maybe X, Y, and Z. And now I'm going to copy this, and we're going to see, I secretly already know, so I'm going to make 2 right now, how many ways there are of orienting this one. I know only because I've done it before, not because of some kind of weird intuition. Okay, so I need to start by orienting all my tie-down bars away from the original graph. So I'll get that. And now you can see I have 3 more edges to orient, and when I go to vertex A, well, it has out degree 1, it needs out degree 2. It has 2 unoriented vertices, so I have, or edges, so I have 2 choices. And so like if I orient the edge from A to B away from A, now A has out degree 2. And if I go to vertex B, I don't actually have any choices there. It has out degree 1 and only 1 remaining unoriented edge, so I have to orient it like that. Same for vertex C. So here I could choose the orientation of the edge AB, or analogously, I could have chosen the orientation of the edge AC, but I only have 1 choice, and that determined all the rest. So the other way of doing it, I would make the opposite choice for AB, which forces me to make the opposite choice for BC, and that forces me to make the opposite choice for AC. So I have 2 ways of orienting this graph. And the rigidity matrix this time looks like A minus B, B minus A, 0. So the first part's the same, A minus C, because it's the same graph. C minus A, 0, B minus C, C minus B. The second part is different. So I have 1 tie down bar at A. I have 1 tie down bar at B, and I have 1 tie down bar at C. So again, I have now a 6 row by 6 column matrix, and I could take its determinant in MATLAB. And what you can do, so maybe check, this is something that you can do, is that take the determinant of both tied down rigidity matrices. Then, so you get a polynomial, factor them. There should be a common factor. And if figuring out how to factor is difficult in MATLAB, I'm not sure how easy it is. The common factor should be um, the common factor should be the determinant of this matrix. It's a 3 by 3 matrix where it's really, if you think about A as A1 comma A2, it'll be A1, A2, 1, B1, B2, 1, C1, C2, 1. So the determinant of that matrix should divide both of the determinants of those rigidity matrices, or the determinants of both of those rigidity matrices. That's right. Okay. Let me know if you have any questions. Okay, I'm going to stop it here.